everyone. I'm Kris Overholt at Coiled. I'm a senior solutions engineer. Today, I wanted to talk with you all about how to run financial workloads on terabytes of data in less than an hour. If you're anything like most of our Dask users that come to us, you might have a backtesting workload or some credit risk analyses that you're running. Typically, these can take on a single laptop or a large VM anywhere in the order of 8 hours to a couple days to run. Because of that, a lot of our folks are running these jobs overnight or over a weekend and hoping that they finish. I want to show you how you can scale up the same code that you're using today, probably using Pandas, NumPy, maybe some different Python tools. And I want to show you how you can scale that up, use your entire data set. I'll show a couple of use cases. So hopefully you'll find it useful. I want to reflect back a lot of the learnings that I've had working with folks in the financial services industry, especially with Python and scaling up their workloads. Quick information about myself, just some background. I work mostly with our enterprise customers, which are usually Dask users, data engineers, data scientists, many in the financial industry. Before Coiled, I was at Anaconda and RStudio and Algorithmia. I got to see kind of what does the end-to-end pipeline look like for data scientists. So been at it for about 7 years now, working in that context. And then before that, many years ago, I was in civil engineering, running fire simulations. So we would do fire research, and I would run large simulations on HPC clusters, 10 years plus ago. So it's always interesting to me to see the evolution of where's compute going, and especially now with the cloud. Hopefully you'll take away some useful tools here about how you can speed up your workloads. So just an overview of what we're going to cover today. First, I'll talk about what's the motivation, like why do we even want to scale up these quantitative workloads? Things like credit risk modeling, backtesting. These are very usually computationally bound, sometimes memory bound problems. I'll talk about how we usually think about, how I talk with users and think about different parameters and why we want to speed this up at all. Then I'll go into some use cases and demos. This is where I hope you'll take away a lot of actionable information about here's how you're doing things today, here's how you can scale up with Dask, here's how you can get a giant cluster like what I've done with Coiled, and try some of these things out. And then finally, I'll go in a little bit more background about why Dask, why Coiled, how do they fit in together, and how do we see Dask users coming to Coiled and being able to scale things up in the cloud, being able to get better performance, and being able to work a lot more closely with the Dask experts at Coiled. So first, let's start with motivation to scale up workloads. Problems when scaling, in particular when you're working with financial data sets, these data sets can often be quite large. It's best if they're stored in some kind of cloud object store like S3 or Google Cloud Storage. Most of the time, these jobs, when you run through them, are going to be either CPU bound or memory bound or both. And I'll show you a mix of that when we get into the use cases. The problem is limited compute resources. So a lot of times, folks are, for data compliance and security reasons, need to run things on their laptop, or they need to run things on an on-prem machine, or maybe they get access to a large VM. And so basically you're bound by, this is the compute resources we have, this is the problem we're trying to attack. And so as people iterate on that with backtesting jobs or training jobs, these can typically, if you're going to run the whole thing, can take hours or days to complete. This may be where you're at today. We did a poll on Reddit asking about, how do people approach this problem? And over half of the users said that they actually use a subset of their data to run jobs quickly. So we've seen a lot where people say, this is the compute that I have. I'd like the jobs to run in a couple of hours. So I'm going to trim down and use 5% or so of the data set. I want to show you a better way of how to think about these problems and to be able to prototype quickly on your laptop, on a cloud VM, or in the cloud. The last bit here that adds into the mix a lot of complexity is there's lots of different Python tooling here. This is typically a good thing, but what it means that you probably have a lot of existing Pandas code, NumPy code. Maybe you're using some of these other tools like stats models. I'll show a use case with XGBoost where you might be doing training and prediction on certain areas, or there are domain-specific libraries like Backtrader, Backtesting.py. The good news that I have for you is if you already have all this Python code, it almost always works with Dask, and I'll talk about that later in terms of pandas data frames, NumPy arrays, and the interaction there. So these are the problems we face. Now, when you're scaling, I like to break down these problems into these factors. Cost is one. How much does it cost you to do a run? Time is another. Does it take 1 hour or 8 hours or 24 hours to run your job? The last one is particularly important, and it often gets left out of the conversation, is how smooth is your development process? Are you having to recode and use your Python code and use it in another language, or work with Spark, or work with other layers coming into play? And how quickly can you iterate? So if you backtest one strategy and you run through that job, how quickly can you backtest 10 more? That's often the difference between being able to innovate on newest and greatest kind of trading strategies or models versus just being stuck and waiting for the next run to complete. So think about these three things: cost, time, developer efficiency, where you're at today. And as you look at the use cases, think about areas that Dask or Coiled could help you there. One thing important about Dask is how it scales. So Dask inherently is a parallel Python framework. And because of that, it's very flexible in terms of it's agnostic of where it's running. So it's very easy to prototype something with Dask, even with larger than memory data, and run it on your laptop. You then take the same code and run it on a large VM or a large machine, maybe in the cloud. And then you can take that and plug it into a big 300 node cluster, something like what I have today to show you running in Coiled. So you can think about Dask and Coiled helps users kind of transparently work between these different environments and move your computations from your laptop, where you work very quickly, on the full data set in the cloud, on the cloud-based cluster. So with those kind of problems and motivations in mind, let's dig into some use cases and demos. I think hopefully you'll see the parts here where Dask is helping and where you're sort of just doing what you normally do in Python and Pandas. So a couple of different use cases here. The first one, and I'll jump over to a notebook in a second and kind of show this live, is we're going to do backtesting on stock data. Backtesting is a very, very common use case. Probably most of you on the call have done or are doing this regularly. In short, backtesting is if I implement a trading strategy or an algorithm, I need to test that on historical data to see how it would have performed. Usually the more the better, the more time the better. Rather than 1 month, I'd like to use a year. Rather than 1 year, I'd like to use 10 years worth of data. So I'm going to show you how you can use Dask and Coil to implement and evaluate a trading strategy. We're going to be using a data set that's consists of 28 different ticker symbols. Each one has about 13 years of high resolution data, and it manifests as about 1.3 terabytes on disk. So what we're going to do is we're going to use the data frame API in Dask, which if you're a Pandas user, and I suspect most of you are, should look very familiar. And then we're going to run that on the entire data set with a 300 node cluster in Coiled. So let me switch over to our notebook and I will walk through exactly that. So the nice thing about this notebook, you should see a clean separation of what's going on with Coiled. By the way, quick mention, if you're not familiar with Coiled, it's a Dask as a service, very easy way to ask for Dask clusters in the cloud. I'll show some of the kind of interfaces of how you create a cluster, what that looks like. So you'll see Coiled showing up. Think of it as just easiest way to spin up a Dask cluster in the cloud. And I've done just that. So the first 3 cells here are, and let me bump up the font size here. So the first 3 cells are related to setting up Python dependencies. So we want to create a software environment that has basically a copy of the libraries that I'm using locally. So you could be running this on your laptop, you could be running this on a cloud VM like I am in this case. So I'm asking Coil to build an environment that has Dask, and XGBoost, and scikit-learn, S3FS. And that way we make it really easy to put those dependencies on a big cluster like the one I'm going to spin up in the next cell. So we've created a software environment. You can use pip, you can use conda, you can use Docker, ideally whatever, just point to whatever packages you're using today. And the second step here is to spin up a cluster with Coiled. So if you've worked with Dask at all, you might know that it has a way of working locally, has a way of working with clusters. You can think of Coiled as just one of those abstractions, and then we're spinning up a cluster in the cloud for you in AWS and GCP, sort of wherever your data lives. So rather than going through 20 or 30 steps with Kubernetes and namespaces or VMs and networking, we're just asking Coil for a cluster and it's giving us one. So here I'm asking for a 300 node cluster with the software environment we defined before, and I'm asking for a certain amount of 32 cores per worker. Make sure my scheduler has a lot of memory because I want to throw it some really big task computations and a few other options. So that's it. And if I flip over to my Coil dashboard, I can see there's my 300 node cluster. It's running. Here's the current cost and where we're at so far. So we're going to be using this cluster in this webinar to run some live computations. The last Coiled part before Coiled goes away and we get on with the Dask computation is just connecting my Dask client for my development environment to the Dask cluster that we spun up. So once we do that, we'll get a link back to the Dask dashboard. So there it is, and we are ready to go. So now Coil is going to go away in the background and it's going to power our 1+ terabyte analysis here. So this part, I'll just walk through really briefly. You are probably doing some flow like this. You can adapt this to whatever tools you might be using. In this case, we're going to read out, we're going to pick one stock ticker and we're going to read 14 years of data, 50 gigs. And if you're a Dask user at all, you know that this hasn't actually run a computation yet. I'm just pointing to and saying, here's 50 gigs of data. Get ready to do something next when I tell you to. So this is what the data looks like. It's all synthetic stock data. So we have open, close, high, low over time for over 14 years. So now at this point, you may be doing something like this in Pandas. You may be using one of those backtesting libraries. Basically, this would be your trading strategy. So here is sort of just a synthetic one where we take a rolling average of 5 points in time, a rolling average of 20 points in time, and that strategy determines if we buy and hold or sell. So again, just made up, but here replace that with whatever trading strategy or algorithm that you would want. You might have that parameterized in Pandas, so it would look very close to this, or you might have an external binary, or you might have some custom code. So this is a good place to think about where that would go. And then we want to actually run the computation. So here, we're going to calculate the return of the strategy. So basically, we're going to look over this entire historical financial data, say what would the returns be given that strategy that I implemented in the last cell. So now if I flip over to the Dask dashboard, you can see some tasks getting set up. So now these, what's happening is that Dask is taking my requests that I put in, the windows, the rolling averages, all those computations, stacking this up as a task graph, sending that to the Dask cluster. And before I finish the sentence, it's run through 50 gigs of data and returned back what the returns would look like on that strategy. Again, this is synthetic data, but the computational load is representative of what would happen. The last part is to evaluate the strategy. A lot of times we take the standard deviation and look at that compared to another kind of a known stock index. And so in this case, another computation is going to run. That's happening on the Dask cluster. And then I'm just getting back kind of the answer. So I don't have to move lots of data here and there. I'm simply just using Dask how I normally would. And the heavy computations are being deferred to the cluster. If I didn't have that big Coil cluster, we would be sitting here for many, many hours as Dask would chug through that on my laptop. Or in the absence of Dask, if I were just using Pandas, I'd probably start to get memory errors at this point. So now that we've kind of gone through implement the strategy, evaluate the strategy, we would want to do this for the entire data set, 1.3 terabytes. Here, I've basically just said for these 28 ticker symbols, iterate through them, do the calculations we just did over all of the data sets. I ran this before, timed it. The computation wall clock time is 37 minutes, which is a bit longer than this webinar, so I won't run this and we won't watch the results. if you'd like, you can schedule a meeting with me. I'm very happy to show you the live version of this running. We just don't have time to in this webinar. The point is, I very easily took Pandas code, parallelized it with Dask, ran it on a cluster, and now I can run, I can backtest on like 1.3 terabytes of data in less than an hour, which is really nice, and it should allow me to iterate a lot faster. I could also probably optimize this code a bit even more. Right now, it's sort of doing a very naive loop and then running some Dask computations and going through again. There's different ways I could do this, but you know, I like messy code and I like throwing that at Dask, and I'm under an hour, so it's not bad for a first cut. So let me jump back over to the use cases, and we'll jump on to the second one. This is a good reminder, if you have any questions, you can post them in the Zoom chat, and we'll get to it in the Q&A towards the end of the webinar. Second demo and use case is something different, credit risk modeling. So in your line of work, you may work with loan processing or credit risk modeling like a lot of users that I talk with. So here, the computational workload is going to look the same or similar, very different use case though, where we're going to train a classification model on 1.3 terabytes of credit and loan records. In this case is 15 billion credit loan records. In this case, we'll be using XGBoost to train on this amount of data, and XGBoost has native Dask functionality, which means we can plug it right into Coiled. So we're going to run this massive training workload on Coiled, similar to what we did in the first example. So I'll skip through this. I'll run through this first part quickly. You've seen something like this already. We create an environment. We create a Dask cluster. I'm actually going to reuse that same cluster that I spun up and connect to it. And then Coiled goes away in the background and waits to run my big computations. So here I'm going to point to 15 billion credit loan records. This is some sample data that's out there on the UCI machine learning repository. So here we're going to load in this data, and again, this part is pointing to the 15 billion records. We haven't yet done anything with it because of the way that Dask kind of waits for me to ask for compute at the right time. The next thing we're going to do is to compute a training matrix. So here I'm instantiating a Dask D matrix pointing to a test train split on this data. So there's kind of two computationally heavy parts here. The first one is constructing this training matrix, and in a second it will send over a pretty massive task graph, and that'll start running on Dask and Coiled. Once that's done, I'll come back to this notebook in a few minutes. We'll train the model, and this overall should take about 5 or 6 minutes. So this one you should see complete in the time here if we have time. So basically what this is doing is training a classifier on 1.3 terabytes of data. You can see the training cell here that we're going to run next. Once that's done, we would do a batch prediction. So the nice thing here is I'm developing locally with XGBoost, and then Dask is sort of doing the right thing at the right time, sending those computations to the cluster, and I'm getting them back. So again, without the 300 node Coiled cluster here, we'd probably be sitting here for a few days watching this model train, or we might run into memory errors in the absence of that. So I'll come back to that notebook and we'll see how it's doing. It should start kicking off the computation in a few minutes, but we'll let it do its thing in the background and we'll come back to it. So with those two use cases, hopefully you saw like that's the actual approach and code that you would use to run through an analysis, like a fairly large scale 1+ terabyte. Maybe your data set's a bit smaller or a bit larger. Same approach applies here, right? It's a nice way to be able to attack these kind of data sets and work with them in the case that we were just looking at, almost real time or less than an hour, get through the iteration and move on. So I want to talk about a few minutes just behind the scenes, why Dask and why Coil, like why is it helping this problem? So number one, if you're not familiar with Dask, Dask is a parallel Python framework. It has a familiar API that maps to pandas, NumPy, and so it should look very familiar. On the bottom right, you see a chunk of pandas code doing a group by and a chunk of Dask code doing a group by. pretty much exactly the same thing. We're just adding, you usually have to think about partitions or chunks or when to compute, right? Other than that, it's Pandas API that you know and love. You can also use Dask on your laptop or a big cluster. It's very easy to swap out what backend you're using in Dask. Dask integrates well with the PyData ecosystem, supports complex applications. I showed an example with data frames, but you could also be using something like Dask delayed or Dask futures and introduce your own custom parallel code. And finally, there's real-time diagnostics like what we saw in the dashboard, and a lot of information about task optimization and scheduler memory, things like that along the way. Where Dask fits in the Python ecosystem is actually relatively low layer. So this is a nice kind of PyData ecosystem diagram where the low level is Python and its core libraries. And then the higher you go in the stack, the more high level the API is, or even domain specific. So you can see Dask is right there near the bottom, meaning it's a core foundational part of the Python ecosystem. And then meaning things on top of that, like Pandas, stats models, XGBoost, can all build and run on top of Dask. So this is a nice part. You don't have to rewrite your existing code. You can take most of what you're doing today in NumPy or Pandas or libraries that use those on the back end and run them on Dask. And finally, when I work with users a lot, we think about when do we use Dask and Coiled. It's very common that a user will come and say, I'm trying to do this backtesting in Dask, and I want to make that run faster and then move on. There's actually other parts of the workflow, data cleaning, maybe running simulations, or even batch prediction, where Dask and Coiled are relevant. So you may be working on one of these boxes in your day-to-day life, and I can almost guarantee there's a way to speed that up with Dask and Coiled, but there are probably other ways, either pre-processing or posts in operations, places where Dask could be applicable, cross-validation, things like that. So I wanted to share this back because you might see other places where Dask could be useful. To wrap up, and I'll jump back to the notebook in a second, in summary, if you're working with financial workloads and you are running into bottlenecks, right, whatever those may be, computational, RAM, CPU, or just having trouble getting started with a cluster, here's some things you can try. So number one, if you're not already, try Dask. There's really good examples at examples.dask.org. We have some in the Coil documentation. So work with Dask, choose the right interface for your use case. Here we used the data frame interface and the XGBoost interface. There's many, many more that you can try out. Store data in the cloud using parallel-friendly data formats. Here I was using CSV. We also commonly work with folks using Parquet, stored in S3 or GCS. There are other things out there like ZAR. So that's a good way to offload a lot of this work off of your laptop or your special networking setup onto a good cloud where you can have much more flexible compute. Start small and scale up. I always suggest start with Dask on your laptop, start with a subset of data for the purpose of setting things up the right way. Then it's very easy to move to a large VM or a 300 node cluster like I showed today. Profiling and performance reports are also really, really important. It's hard to tell where bottlenecks are happening if you don't know exactly what's going on. So there's something in Dask and Coil called performance reports. It's a really easy way to snapshot your parallel run and get back some of the plots, like on the bottom right, flame graphs of what's taking up the most time. Are things getting slower or faster given my most recent update? That's a great way to snapshot that. Finally, with that information, it's nice to perform a scaling and cost analysis to figure out if I double the size of the cluster, how much does that cut my runtime? What does that cost look like? Is the area under the curve preserved? You can really start to see, like, you can start, instead of saying, how much can I limit the data to get this to run quickly, you can actually start to say, what size of a cluster can I run in order to meet my SLA or the desired runtime? And the reason I talked about under an hour is that most of the customers we work with, like you and users, come in with, this takes 8 hours or 24 hours to run, and almost always we get that in under an hour just by plugging in Dask at the right place and Coiled in the right place. So some other Dask best practices here you can take a look at.
Yeah, there's a few questions I want to run through with you.
Yes.
Hon Yin is asking, I presume the parallel tasks are scheduled to run Dask on multiple nodes machine clusters. Do you need to set up the total nodes up front, or can these be dynamic allocated. I am also not sure if Dask / Coiled are open source or commercial offering. So let's start with that.
Yep, great question. I don't see that one in the chat, but I think I got enough from your summary. Thank you, Adi.
I actually started with the last one. It's funny.
Gotcha. Oh, there we go. Thank you. Perfect. Yes. Thank you, Hanyin. Great question. So I'll answer two parts. First part is so today I was showing, like, let's start a 300 node cluster and use it for both use cases. So there's a few ways you can ask for a certain number of workers. You can ask for a certain number of CPU and RAM like I did. Or if I were actually putting this into production, Dask has an adaptive scaling method. So most of us would just call that an auto scaler. And you can plug that into Coiled and say, hey, I'd like a cluster between 0 and 300, and based on the actual back pressure, the actual workload, scale it up and down. So that's a really nice way. In that case, you don't have to pre-allocate exactly how many workers you need. And so that auto scaler, you can use that in Dask, you can use that in Coiled, and it will sort of just take care of the resources. And then on the question of open source or commercial, so Dask is an open source project. There are many, many tools around Dask that are open source. Coiled is a commercial offering that helps you scale that up in the cloud. So you can think of Coiled as offering three things. Number one is Coiled Cloud to run computations like what I showed today. Number two is guidance to help make sense of all of the different packages and approaches and performance that you might want to gain. And the third is support. So if you need support and SLAs around Dask, those are the three things that we do. So hopefully that disambiguates. What does Dask do? What does Coil do? Thanks for the question.
There's a couple of other questions there in terms of the size of the data. If you can pick one, there's a couple that kind of.
Yeah, for sure. I'll go in reverse order here. There's a question that you use Dask for your workloads, and can Coil provision specific hardware? Can it use spot instances? These are really good questions. The short answer is yes and yes. In Coiled, there is actually, I'll answer that out in our docs. If you want to look at creating a cluster, there's a few different ways you can do it. By default, you can ask for a number of workers. You can also ask for a custom amount of CPU and RAM. If you want more control, you can actually specify an instance type or a list of instance types. So a lot of our customers, especially in the financial space, will say, I want this family of instances because I know it has high IOPS and high network throughput. So you can do that in Coiled. And yes, we have a flag for on-demand by default or spot instances. And as the Dask users know, Dask is resilient to worker failure. So spot instances are a great way to save like 70, 80, 90% and spin up a huge cluster like what I did today. So yes,
and this
those are all
a question
supported.
by Harold, right?
That's right.
Question.
Okay. Yes, exactly. Yep.
And then there is the very first question. It kind of repeats itself a couple of times. It was sent just to you and me, but maybe you can respond to that. 256 gigabyte for scheduler seems really high. Can you explain why you would need so much?
Yes, that's a great question. So whenever you work with distributed computations, as you know, things get more complex. You have more knobs to think about in terms of the parallel problem. Sometimes the scheduler, because you're sending big task graphs to the scheduler, and then it's fanning these all out to the workers, sometimes the scheduler itself can become a bottleneck. So out of the two use cases I showed, backtesting is actually CPU bound, not so much memory bound. So it's not really for that one. The XGBoost problem is CPU and memory bound. So you're in the kind of like highly complex, challenging problem. In that case, I basically gave some safety factor there, but XGBoost, when it does that training, is using, there's usually some overhead with Pandas data frames and memory versus on disk. XGBoost has quite a big overhead there because it's setting up a training matrix. It's setting up a pretty complex computation. So I generally found that 64 or 128 gigs would work. I wanted to make sure it went super smoothly, so I built in a little safety factor for the webinar. But if you ever see, there are ways of looking at your scheduler, looking at its CPU saturation or its memory saturation. If you ever see that, it might be a signal to bump up. The opposite of this I see a lot is very small schedulers, right? With 8 gigs of memory, that most certainly wouldn't be able to run computations like what we did today. So great question.
Hussein was asking, have you been able to use Dask real-time streaming data in brackets stocks?
Yes, yeah, that's a great question. A lot of our users will, it's yet another area of options, right? So most commonly, our customers will work with streaming data that's happening upstream, and they're running Dask either at some interval or hooking that into the stream. And there's a bunch of different ways to do that with Kafka and PyKafka and Kafka streaming. There's a number of other tools out there, some of them more Python native, and then some that just hook into streaming frameworks. So short answer is yes, it's a great, like Dask, we see Dask used for streaming and for batch analysis for sure. Mostly batch, just given the nature of the industry and how things work, but certainly high frequency trading or other customers are using Dask with streaming data.
Excellent. Manuel is asking, hi Kris, how do you actually estimate the memory/processing resources that you need for your computation?
That is a great question. There's a couple of things that I do. The sort of the data scientist, data engineer in me, after talking so much with users, we'll think about what's the full data set size on disk, and you basically add it, multiply in some overhead, right? So if I have terabyte of data and I want to do some computation on that, naively you would say, well, maybe Pandas has 4 times overhead, so I need 4 terabytes of RAM on my cluster. However, Dask chunks and stream things from disk and from object stores, right? So it's not a direct calculation, but it'll give you a back of the napkin of like, the biggest thing you want to determine is, will my code run or not? And in some cases, you will get memory errors if there's not enough in the absence of Dask, right? The other thing is your code might run, but it might take 8 hours, and that's not optimal. And then the third bin is I want it to run faster. I want it to run in under an hour. So you can get a back of the napkin just by taking your data set size, building in some multiple for overhead, and going for there. The second part, the engineer in me just sort of spins up something, sees what's bottlenecking, and then goes up or down from there. So Coil makes it really easy to say, give me a 200 node cluster, I'm gonna run this computation, what went wrong or what's bottlenecking, let me scale up 100 nodes or down 100 nodes. Once you lock in on that, you can parameterize that or set it to auto scaling from that point on. So it's usually just something you do initially and then kind of stabilize for a given workload.
Wonderful. Joey's asking, I noticed you spun up a big 256 gigabyte RAM, same thing, scheduler. I've never been able to get task graphs less than 20 gigabyte to run to completion. Can you explain any tricks to utilize that large of scheduler?
Yeah, it's a good question. Here, most of what I did today, what you're looking at kind of a first cut of what I would do. So that schedule, like if I look at the scheduler profile, it's actually still bottlenecking on CPU. So initially I was asking for more scheduler memory. I think the default was 8 or 16 gigs, and I really need 32 at a minimum to run my computation. At some point, that option that you saw where I asked for larger scheduler memory actually became me asking for more cores, right? So it was actually the scheduler was getting CPU bound. So initially I cared about memory, then I cared about cores. That's probably why you're seeing that go up higher than what you're used to. But basically, there are some Dask best practices about dealing with the scheduler. There is a tab in the Dask dashboard that looks just at the scheduler, what's going on in CPU, RAM, and the scheduler. In general, when you're working with task graph, it's a good idea to work with 500,000 tasks or less. If you're generating more than that, there's probably some things you can do to break that up even more, so you don't have to ask for such a giant scheduler. So here, you can consider that the engineer in me, that's just kind of big safety factor. I needed a minimum of 32 or 64 gigs of RAM, but I really needed more cores later on, especially for the XGBoost computation is particularly challenging, and setting the high scheduler and the higher worker, I think I had 32 CPUs per worker, made that really smooth, no errors, so that you're seeing a little bit of that iteration in first cut. I would want to drill in a bit more if I were productionizing this.
Another question from Paul. Can you talk about Dask RDDS session IDs and re-execution of task graphs / lazy branch execution?
Yeah, sure. So in Dask, there's a lot of wonderful documentation in the Dask docs. In general, Dask and Dask is powered by a DAG engine. So every interface that I use in Dask, whether it's a data frame or an array, is going to generate a DAG and a task graph and then send that. When the user requests computation, it's going to execute that, distribute that to the workers. This is very, very similar conceptual model to Spark and many other things that are powered by DAGs. So most of what you see Spark would do, Dask would usually do a similar approach. The biggest difference is just that the runtime, right? PySpark is going to serialize that to Scala, run that on the JVM, possibly in a Yarn container. Dask is going to do that in pure Python and execute that to a pure Python Dask worker. So really, it's just an implementation detail. Things like re-execution, lazy branch execution, you can look through the Dask docs and see generally the data frame operations, array operations, bag operations. Most of those are going to be lazy computations until I put in the dot compute, like you saw in my notebook. There are a couple of other interfaces like delayed, Dask delayed, and Dask futures, which are lazy and eager, respectively. So a lot of times, quants will take one of those interfaces and then wrap that around their custom parallel code. So you actually have some freedom, especially when you go to the lower level APIs in Dask, to specifically handle things lazy or eager when you want to. But on your question, there's a lot of really good Dask docs about re-execution, lazy branch that I encourage you to take a look at.
Excellent. And guys, we may not have time to respond to all the questions, so I just put in the chat a meeting calendar. Just feel free to just click through it. I think maybe last one, Darren is asking, Kris, can the PyData libs and a coiled cluster run on ARM64 in brackets Graviton 2?
Yeah, it's a great question. So usually the answer for this comes in two parts. If you were using Dask, you could spin up an ARM cluster and kind of go at it and see what works, see what doesn't. In that case, you'll have to handle dependencies, make sure everything works on the ARM architecture. At the moment in Coiled, you're not the only person who's asked. We've been working with a particular user or a group of users that says, they're getting a lot more bang for their buck out of Graviton. So we're very interested. So in theory, the Coiled part is just standing up instances and standing up Dask. The one part that we want to test out fully is just to make sure that the Python package story there is clean. As you know, any bumps in the road that you might experience with Python packages, like if that goes on a cluster, it'll amplify the problem. So what I would do, so we've taken your feedback. If you're interested in Coiled and ARM, please reach out to us. We're very interested to talk to you, see what you're doing today. I would try things out in Dask, and then it's sort of a work in progress at Coiled. So you all will be the first to know when you can run on ARM. One interesting thing to note is we just unlocked, so in Coiled, you can specify instance types. While we were starting out, there was kind of a short list of instances you could spin up. A few releases ago, we enabled you to spin up any instance type on AWS. And so if there are other specialty instance types, ARM is a special case because of the architecture and packages, but if there are instances you've been really interested in trying out, just haven't got the time to, log into Coiled, print out the list. I think it's some 600 instance types, spin up a cluster, and let us know how it goes. We always learn interesting things when people